right, this is the final talk of this session before our tea break. It's titled Solar versus Diesel, Where to Draw the Line for Cell Towers, and it's presented by Talal Ahmad.
Yeah, sorry for that. The internet got disconnected somehow, so we had to connect to some other network. My name is Talal Ahmad, and I'll be presenting our paper titled Solar versus Diesel, Where to Draw the Line for Cell Towers. My co-authors in this work were Shankar and Fareeha, and we were advised by Professor Lakshmi Subramanian. So a regular cell tower is often seen as just a tower with a few antennas, but it is made up of multiple components. Based on our data, a typical cell tower needs around 3 kilowatt, between 3 kilowatt and 20 kilowatts of power. Cell towers usually operate at lesser power in cities to reuse spectrum in neighboring cells. So depending on where they are located, they'll use between 3 kilowatts and 20 kilowatts of power. Here is a power breakdown of different components in a regular cell tower. If you can, yeah, it's really small, but okay. So the major power consumption is by power amplifiers, which consume around 60% of the power, while 17% is spent on cooling equipment for these power amplifiers, and 10 and 13% is spent on signal processing and power supplies, respectively. During the course of this presentation, I'll be referring to this cell as a big cell. We obtained some operational data from a cellular provider in a developing country and use it here to demonstrate the amount of grid failures that are faced by cellular sites in developing countries. So the data is from over 1,000 sites, and these sites are all from these sites were all operating in the same region. It's not like they are from different regions. The first column basically shows the range for which grid power was missing, and the second column shows the percentage of sites that experienced that grid failure. For example, around 11% of the sites experienced less than 2 hours of grid failure. What is really alarming over here is that around 19% of the sites faced more than 10 hours of grid failure in a single day. And in extreme scenarios, grid failures can last for days in developing countries. To deal with this problem, diesel generators are used in all of these cellular sites. And even if grid power is available to these sites, it is highly fluctuating. So a wireless company in South India reported that a grid supply of 240 volts can vary from minus 1,000 volts to plus 1,000 volts, which leads to device failures. So in essence, there is a heavy reliance of on diesel to power base stations in developing countries. And this high dependence on diesel made telecom sector the 4th largest importer of diesel in India in 2013. This statistic was reported by Petroleum Planning and Analysis Cell of India. Telecom sector was behind transportation, farming, and industries. But still, it's a pretty big thing that they were like the 4th biggest importer of diesel. Similarly, so the reason for this high consumption of diesel is not just that grid is missing, it is also because diesel generators have extremely poor efficiency. Theoretically, they are supposed to have 45% efficiency, but in reality, in practical scenarios, they only typically have 15% efficiency. So we got some diesel consumption numbers from a cellular provider, and this data is aggregate for around 1,000 sites. The table shows that hundreds and thousands of liters of diesel is combusted every month, with the month of May taking the lead. So this happens typically because during summer months, lesser power is available from the grid due to more household load. And this amount reduces during the winter months because grid is more available on account of household loads being less. This dependence on diesel has a direct impact on costs. This affects the consumers, and it can lead to them cutting down on their communication needs because of the high cost. Dependence on this dependence on diesel and lack of stable grid, when combined with low population density areas, can lead to huge areas, lead to big gaps in cellular coverage. So this is because it is not economically viable for commercial cellular providers to go into areas with low population density, considering the cost they have to spend in terms of diesel and infrastructure. This fact is also demonstrated in these two figures. The figure on the left shows cellular coverage of Kenya a few years ago, and the figure on the right shows population density of Kenya around the same time. A direct correlation can be seen between population density and cellular coverage. So all this rant about diesel leads to the question that why don't we just start using solar to power these base stations? And the fact of the matter is that big cell design is extremely power hungry, and the watts produced by solar panels is still pretty low. So if you want to power a 20 kilowatt base station, and the sun is available for around 8 hours a day, then you basically need 12,000 square feet of solar panels to power that, which is basically equal to around 3 basketball courts. Not to forget the huge battery bank that will be required to store all of the energy. And you need even more solar panels and batteries if you want to cater for cloudy days, for instance, or for unexpected demand in coal load. It can also be argued that why don't we just use solar to power grid failures? It tries to show how much power solar panels need to produce per hour to cope with different grid availability levels under different call loads. So the distribution P on the right, P if you can see the legend, so the distribution P refers to the distribution of call load, while the distribution K refers to the distribution of grid failures. And both these distributions are based on actual data that we obtained. So given a cell tower rated at 6 kilowatt, it needs 6 kilowatt at maximum load. If we want to operate it with 95th percentile of grid failures, while supporting maximum load, the panels need to produce around 16 kilowatt of power every sun hour, which is basically equal to like 1 basketball court instead of 3 now. This is easier said than done, right? For the same cell tower, around 8 kilowatt is required to cater for maximum load with average grid failures. Similarly, a little less than 8 kilowatt is required to cater for average grid failures and average expected call load. And in essence, the grid failures are so unpredictable that it is extremely difficult to provide any guarantees, any reliability guarantees using just solar. So if the big cells can't expand into rural areas because of their dependence on diesel, and we can't power these big cells with anything else other than diesel, what else is out there that we can use? We have the option of using these small cells that provide all the functionalities of a big cell. Except that these support lesser number of people and have a smaller coverage area. By smaller, I do not mean that the coverage area is in meters. It is pretty much comparable. They are basically micro base stations, and the range that they cover is still in kilometers. But the important thing to note over here is that the power requirement of these small cells is orders of magnitude less than a regular power station. So for instance, this picture is of a unit that we have in Ghana right now. And this picture is of a unit that we have in Ghana right now. And based on the power requirements that we have measured on this unit, it takes at average 300 watts to power this kind of a unit. So this seems to be an ideal option if we want cellular networks to be solar powered. But the only problem is that they support lesser people, so we can't put them everywhere. So what is it that we do in this paper? We try to provide an economic framework to evaluate the conditions under which grid-based power stations are the best options, and the conditions under which we should use either diesel or solar. So we take into account several parameters in our economic framework. The parameters that we use in this framework include cost of diesel and grid power. We also take into account population density, diesel transportation costs, and land rent for putting up solar panels. We make some simplifying assumptions. For example, a base station is going to be powered by single source. But we capture all macro-level parameters that are important, like distance from a city and population density. So in the next couple of slides, I'll try to go over the modeling hypotheses and important parameters. For exact details, please refer to our paper, because the write-up in the paper is much more detailed. So the hypothesis that we try to evaluate using our modeling is that there are 3 operating regimes parameterized by distance from urban center. So the center of the circle over here refers to a particular urban center, and there is a radius RG to which grid power extends. And this is basically the area in which it is feasible to use grid. Beyond this radius, we assume that diesel is used to power base stations, to power cell towers, because there is no grid power. But using diesel is feasible only up to a particular distance. We hypothesize that there is a boundary seen in this figure as the dotted line, after which diesel is no more feasible, and solar becomes the most viable option. We refer to this distance as crossover distance. And this crossover distance term will come again and again in the next few slides. And it's important to mention over here that we model all costs as a function of distance from the city. This is because the distance captures important parameters like population density, land rent, and transportation costs for diesel. Several land rent studies have shown that the prices of land rent reduce exponentially as you move away from the city center. Similar trend is shown by population density, while the transportation costs increase linearly as we move away from urban centers. Transportation is really important in this context because cellular sites can only store a limited amount of diesel. So it has to be transported periodically to the rural site. If they can afford a pipeline, they might as well just extend grid by laying wires. Another important thing that we incorporate in the model is the capacity of big cell in comparison to small cells. We use the ratio of big cell capacity with small cell capacity to incorporate this in our model. So the cost of solar-powered small cells and diesel-powered big cells are both dependent on R, as I've mentioned. And to determine the crossover boundary, we equate the total cost, and after canceling out, we get the following equation. I've tried to highlight the parts that are dependent on R being the distance from the urban center. Left-hand side is the cost of solar-powered small cells, and right-hand side is the cost of diesel-powered big cells. The left-hand side is exponentially decreasing as R increases, and the right-hand side is linearly increasing. So there will always be a solution to this system. This slide basically shows the plot of cost of solar and the cost of diesel. R is given on the x-axis, while the cost in rupees is given on the y-axis. It can be seen that the crossover distance in this case is 6 kilometers from the city, based on the parameters that we used. This means that after a distance of 6 kilometers, it basically becomes feasible, it becomes more economically viable to use solar-powered small cells, rather than use diesel-powered big cells. Not that the exact value of 6 kilometers depends on the parameters that we have used. This value will change with different parameter setting. Our contribution is an economic framework to study the trade-off between solar and diesel, and the framework itself remains unchanged while we use whatever set of parameters we choose to use. So this figure basically shows the crossover boundary on the y-axis now, and how this crossover boundary changes with cost of solar on the x-axis. The different lines in the graph are basically coarse grain changes in the price of diesel. This figure is meaningful in context of future trend for solar. So the future trend for solar is that there is a huge increase in investment in solar. And the solar technology itself is becoming much more robust. So the solar panels that were supposed to work for only 20 years previously have now a longer lifetime. While the solar equipment will be unstable for longer time, will be usable for longer times, the underlying physics of the solar panels has not changed. So it is not expected that solar panels will exceptionally will automatically just start producing more power, which means that the need for area to put up solar panels is not going to reduce in future. So which brings us back to this graph. Because solar panels are going to have longer lifetimes, the amortized cost per day for powering small cells with solar is going to reduce. Which means that the crossover boundary will become nearer to the cities. It will be more feasible to put solar-powered small cells near the cities instead of farther away. Similar to the last graph, this graph shows how the crossover distance will vary with ratio of big cell power with small cell power. Different lines again represent the coarse variation in diesel price. It is important to put this in context with the future of cellular tower design. Newer designs of cell towers, like Ericsson's tower tube and capsule site, and flexi-based station from Nokia are being promoted. All these sites have one thing in common, which is that they consume lesser power than regular base stations. If you just focus on the hardware, then power amplifier hardware is itself evolving. Newer designs based on digital pre-distortion and envelope tracking for wide band signals are being used, which consume lesser power. And it's important to recall that power amplifiers are the biggest consumer of electricity in a base station. And people are also trying to achieve power savings using soft switches in core routing of cellular networks. So if we put this in context with the figure shown, it can be seen that the ratio of big cell power and small cell power will reduce, and the crossover boundary will increase. In a sense, we'll be able to power big cells with solar closer to urban centers. And in conclusion, I would just like to say that in this paper, we gave an economic cost analysis framework for comparing solar-powered small cells with diesel-powered big cells. This framework uses distance from urban centers as a core parameters, and this model is simple and captures all macro-level operators effectively. We also used operational data to provide evidence for the gravity of situation with respect to diesel across multiple dimensions. And the last sentence that I want to say is that without changing power requirement of cellular sites, and using current big cell model, it's not going to be feasible to power these things with anything but diesel. So what needs to happen is that the newer site designs and hardware that is being produced needs to be adopted by telcos so that we can reduce the diesel footprint of telecommunications in developing countries. That's all.
Okay, we have time for just a couple of questions.
Hey, Talal.
Hey.
So, considering there is grid power in the urban areas, why can't they just battery back up the sites in urban areas instead of running diesel?
Like I showed, right, grid power is extremely unpredictable. The grid power failures are extremely unpredictable. It can be there for, so it will happen, and I've experienced this myself in Pakistan and in Ghana both, that it can happen that one day you'll get 2 hours of load shedding, and the next day the whole day there'll be no power. So the batteries can store a particular amount of charge, right? And so how do you plan for such a scenario? Do you go offline? Can they afford to go offline in an urban city especially? So that's the reason they can't use anything but diesel power. So they need to have diesel generators on all sites.
I've got another a question in terms of my following of your calculations were that the smaller cells will eventually move further into the urban core as the solar capacity and so on increases. But those smaller cells, do they have the same characteristics as the large cells? In other words, correct me if I'm wrong, but these are usually GPRS and they have a smaller footprint and can carry fewer simultaneous conversations?
Yeah.
So, in other words, you're moving them into tighter, more and more dense areas, but with a not as full a service offering as the large cells. Okay.
Yeah.
So but that wasn't included in your calculation.
So I basically, so when I was discussing the last graph, I basically said 2 things. One, the first thing was about the trend that is being followed by the vendors itself, right? The vendors itself are interested in reducing the power footprint. And instead of bringing those cells back, I know that they use fewer channels and they don't have the same capabilities. But the vendors itself are trying to change their own design. So those sites then they can be solar powered. So then this analysis will not work in that scenario, right? So that's what I should have like separately mentioned probably. Yeah.
Hello, this is Rifat. Thanks for your presentation. In the previous response, you just said that there are power failures in the whole day or something like this, and people need to, use diesel or something to, for those power failures. Yeah. So how do you know that people actually need powers the all day, and they need something for shielding those. Did you talk to the people that do you need power all day, or can you afford if you don't have power?
By people, do you mean the operators or the people who are using the network?
Yeah, who are using the networks.
Like you're asking that do people even need the network all day?
Yeah.
Oh, okay. So all these sites, cell tower sites that are like, so we got a particular data set, and one of the characteristics of the data set was that some of these sites are equipped with intelligent load management systems that will automatically turn the site off when there's no load. Okay? So it's kind of the responsibility of the cellular operator to make sure that if people are not using it, he should reduce the power that he's operating on. And some of the sites do it. But again, this is not widespread. This is not, we got data for around 1,000 sites, and only a few of them had this functionality. So yeah, I hope I answer your question.
Okay, you just got some statistical data from the third parties.
Not
right?
third parties, the actual operators.
Okay, not from the end users.
No.
Okay. Thank you.
Yeah.
All right, we're out of time. Time for a tea break. Thank you to all of our speakers.